Hello guys, welcome back to another video on my channel. Uh, this video is probably gonna be the last one I'm gonna record from USA because I'm flying back home pretty soon actually. But that doesn't matter. We're here to do math. I urge you guys to really watch the last video because the last video is essentially a concept or an integral that we're really gonna build on. Especially the fact that we know what last time's integral evaluates to. Because I'm gonna write the question down, and I hate to do this, but we have to use something that we know from the last time. We can't really go for first principle with this one. So it looks like this. I'm calling it I, integral from 0 to 1, 4x squared plus 4 squared x squared x to the 2 to the 2, basically. 4 cubed x to the 2 to the 3, 4 to the 4th, x to the 2 to the 4th, and this is infinite. And maybe I want to move this to the left a little bit, yep, because there's more. It's not over. There's natural log squared of x divided by 1 plus x times x dx. This is the horrible integral. How in the world are we going to do this? Well, I urge you guys to go back to the last video where we actually derived the result for, I don't know, maybe let's call it I prime. We had integral from 0 to 1, x to the s minus 1 over 1 plus x dx. What we can do is we can sort of rewrite this. We have x to the s divided by, we can bring the x to the minus 1 in the denominator to just become an x, and 1 plus x dx. Fair? Well, we know what this was. Watch the last video. I urge you again and again. Digamma of s minus the digamma of s over 2 minus natural log of 2. Well, the thing is we match the denominators in both cases. We have a sum for the numerator for the white integral I. We don't really have a sum here, but we have some power of x. We can multiply some power of 4 later and then sum them up. But we're actually going in the right direction. You can see just by the structure of the denominator. The only problem is, and people might complain, is the natural log. There's no natural log here. Well, there's a really nice solution for this. If you consider this, say, maybe I prime is bad notation, maybe. Let's say j. So, say if j is like a function of s, and it clearly is. Digamma is taken in input of s. Then if we differentiate with respect to s on this integral expression, inside the integral we're going to have x to the s, like d over ds of x to the s. Let me write that down for the sake of clarity. Divided by the same junk in the denominator, which will it be independent of s because it's all x terms. I'm just using Leibniz rule, so the derivative went inside. Now, so if we have something like a to the x and we take a derivative of that with respect to x, we're going to have a to the x times the natural log of a. So in this case, we're going to have natural log of x times x to the s over x times 1 plus dx. That's, well, j prime, j double prime, because we have a log squared there. We take a derivative again to get a natural log squared of x to the s divided by x times 1 plus x dx. Well, what do we do after this? Well, we can do a nice thing. Notice that the powers of x are kind of weird. You can represent them as, say, 2 to the I, where I is the power. This is the power of x. So power of x here is s. So I want s to be of the form to the 2 to the I, where I is some integer. So going from positive integers. So it'll start at 1 and go till infinity basically. So I is some positive integer. If we do that kind of change here, we totally can. Or maybe let's just say this is n for the sake of clear notation. We can totally do that. I'm just plugging this for s. That's all I'm doing, because we claimed this was a function of s, and s in this case is, say, 2 to the n. Now, well, this is just the integral part of it. We also need to to see what this integral evaluates to, we need to differentiate 2 times this boy here, because that's what this integral evaluates to. We differentiate the integral twice and plug 2 to the n for s. We need to do that here and then plug 2 to the n for s. So maybe I'm going to do that in a different color. This is the other side of the world. So, well, I'm going to, the derivative of digamma, I'm going to write as this. This is the nth derivative of the digamma function. So you can call this a polygamma of order n. We just need a second derivative, so n equals 2, and maybe I shouldn't use n, maybe capital N is a better choice here. So with that in mind, we have second derivatives. So this first term is going to be polygamma of order 2, I think. Yep. Of s minus this is again j double prime of s minus, well, we have to do a little chain rule here. So when we differentiate once, we have to divide by 2. We differentiate twice, we have to divide by another 2. So that becomes a 4. This is just the chain rule, because we have s over 2 there. We need to account for that 2 twice. And a natural log of 2 is a constant, so just a first derivative would get rid of it. So this is what we have. This is what the thing evaluates to. We can plug 2 to the n for s to get this expression. Say 2 to the n minus 1, because we're dividing by 2 there. Now the only thing that's left is, well, we fix the powers of x. Forget the summing for now. Let's just try to get one term of the sum. So we fix the power of x. We can get those sums by basically summing over n, small n. What we did not fix was these corresponding powers of 4. They're also rising. So if you notice, we have 2 to the n for the power of x, and that n corresponds to also the power of 4. If we're going to sum, we need to match those things together. So we need a 4 to the n. We need to multiply everything by 4 to the n. That means this green integral and its blue result. So maybe I can do it in a red color. So all I'm doing is just multiplying both sides by 4 to the n, j prime of 2 to the n. So that gives me integral from 0 to 1, 4 to the n, x to the 2 to the n, natural log squared of x divided by x 1 plus x dx. Well, what's the result of this? We also need to multiply by 4 to the n here. So 4 to the n digamma of polygamma of order 2 at 2 to the n minus 4 to the n divided by 4. So 4 to the n minus 1. polygamma of order 2, 2 to the n minus 1. There you go. Now all that's left to convert from 4 to the n j double prime of 2 to the n, from that to say I that we started with, is just to sum from n equals 1 to infinity. Let's recreate, because natural log squared and the entire denominator is constant for the entire sum. So I happens to be, and I'm reverting back to the original white color that we started with. I just happens to be sum from n equals 1 to infinity of 4 to the n j double prime of 2 to the n. We know the result of that. It's sum from n equals 1 to infinity. Maybe like a little bigger or more magnanimous. We have 4 to the n polygamma of order 2, 2 to the n minus 4 to the n minus 1 polygamma of order 2, 2 to the n minus 1. That's fair. That's fair. Now the really nice thing, or by construction of this question, the really nice thing about this was, if you try to write the individual terms of this infinite sum, maybe I can use this. So for n equals 1, I have 4 polygamma of order 2 of 2 minus this. I'll just have, I believe I'll just have 4 to the z, which is a 1, and then this is a 2 to the 0, which is also 1, and then if I write other terms, for 2 I'm going to have this, order 2 is 4 minus, this is going to go back to what we had for the very first term. So 4 again of order 2 of 2, and then so on. This pattern repeats, but the idea is this is a telescoping series in the sense that this is going to cancel with that, this is going to cancel with a term here, and maybe let's write the capital nth term. We always need to worry about these boundary cases. So we have 4 to the capital N polygamma of order 2, 2 to the capital N minus 4 to the capital N minus 1 polygamma of order 2, 2 to the capital N minus 1. Well, by the way this, the cancellation happens, this is going to cancel with the term before it. So all we're going to be left with is the second term of the series, which because it couldn't cancel with something that was behind it, and then the second last term of the infinite series, because it couldn't cancel with something that was ahead of it, because the series terminates for some capital N. Maybe capital N goes to infinity, but that comes later. So we can go back and we can write everything again. Everything else cancels. Just these two terms really remain. So finally, we're going to have just these two terms. I'm just taking the limit as n goes to infinity as promised, because it's the last term and it's an infinite series. We need to do that. We have the second last term, 4 to the n polygamma of order 2, 2 to the n minus polygamma of order 2 of 1. That's fair. Well, this we can figure out. The polygamma of order 2 at 1 we can figure out. We can use some tables for the polygamma of order 2, or we can just look at the series representation for the digamma, and then and then we can basically just take the second derivative and then work it out. We could totally do that, but there's I would say this limit is non-trivial. The limit is non-trivial because this is not a limit you will learn when you're learning limits. You learn sine of x over x is x goes to 0 is 1. You learn that, but you won't learn this. These functions are special functions. So let's just look at this a little more professionally. Let's grow up a little more from high school. So I'm gonna do what's called asymptotic expansion. So, well, we know digamma of x is minus Euler-Mascheroni constant plus sum n equals 0 to infinity 1 over n plus 1 minus 1 over n plus x. Well, now as x goes to infinity, and that's literally what happening here. The argument here is going to infinity. Well, the idea is as x goes to infinity, well, this is sort of, you know, going really, this is gonna grow real fast. So if this term essentially goes to 0, if this term essentially goes to 0 as x gets larger, because x is going to dominate over the n for a finite n, we can ignore this term, and what remains actually is sum from n equals 0 to infinity of 1 over n plus 1 and minus Euler-Mascheroni constant. So this is just the harmonic series, right? Now the Euler-Mascheroni constant was defined as, well, the harmonic series minus limit as n goes to infinity of natural log of n. So if we have this series here, maybe let's just flip these signs to agree with what we have here, and then we add the harmonic series. We're going to be left with some log which has an infinite argument in it. Now the only thing that is in our control, we can't just introduce a separate limit. The only thing that's really like assumed to grow to infinity is x. So we're going to have a natural log of x as the dominating contribution out of all of this. This was really hand wavy. I'm sorry if you wanted more rigor, but this is the way I think about this. And we want some lower order terms, but how will the lower order terms look like? Well, 1 over x, because, well, we accounted for the finite n and infinite going x case, but n is also eventually going to be infinite. That's the, you know, because it's an infinite series. So basically that takes the form of 1 over x, because then the denominator is, you know, basically going to be x plus x if n and x grow equally, or if n dominates, it's still going to be some 1 over n factor. So by and large, it's going to have a form of 1 over x, and this is capital O notation right here. So this is the idea. Now, why is this really helpful is because, well, we can take the second derivative now. So that's going to give us 1 over x and then minus 1 over x squared, the second derivative of natural log. Well, these terms, they don't really matter. I'm not gonna write them out. Maybe I should. Maybe I shouldn't. But they're gonna have this form, because you differentiate 1 over x, you get a cubed in the denominator. We can multiply x squared on both sides, because that's what we had here in this limit. If x was 2 to the n, then x squared will be thought of as 4 to the n, right? So that's why I'm multiplying by x squared. So you have minus 1 plus O of 1 over x, because x squared and x cubed sort of cancel out. It is all in the limit as x goes to infinity. All this asymptotic expansion is assuming really large x. Okay, that's fair. How does it help? Because we can plug what we think x is. So x is 2 to the n. And since n is going to infinity, x is also going to infinity. So that assumption is satisfied. So 4 to the n, polygon of order 2 of 2 to the n is going to be minus 1 plus this contribution. But since n goes to infinity and x will also go to infinity way faster, this can be ignored. So we just have the limit. So when we take the limit, those big O contributions really disappear, because then the asymptotic expansion becomes the perfect approximation. It's not even an approximation. It is the genuine thing at that point. So then we're gonna have a minus 1 out of there, and to find the value of the polygamma order 2 evaluated at 1, we need to go back to this, and we need to differentiate it twice. And when I differentiate that twice, I get an equivalent series, infinite series representation of polygamma of order 2. Notice the harmonic terms go away, Euler-Mascheroni goes away. We just have one singular sum from n equals 0 to infinity, minus 2 over n plus x cubed. This is just the power rule. You evaluate that at 1, sum from n equals 0 to infinity, minus 2 over n plus 1 cubed. You can reindex everything. One over n cubed. And this, my friends from all ages, is the Riemann zeta of 3. So we can just put all of this together. We have a minus of the limit, so we'll have a plus there. Or no, it's a plus of the limit, so we have a minus 1 there, and a minus of this minus. So finally, it gives me immense pleasure to write the big answer down. 2 times Riemann zeta of 3 minus 1. That's the value for this crazy integral that has this infinite tetration kind of looking series for x inside. This is 2 times Riemann zeta of 3 minus 1. There we go, we solved it. Damn, this was a long one, but I think it was worth it. Definitely worth exploring the integral in the last video. Even that video got kind of redundant. Didn't make such an easy question for that. But I think this is a really, really nice result. Peace out. See you in the next video.